Hello, everyone, and welcome to today's webinar in the CERDP and ESCCP webinar series. My name is Rula Deeb. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of CERDP and ESCCP. I will be facilitating today's call. This event will consist of a brief overview of CERDP and ESCCP, followed by the technical portion of the webinar, which features DoD efforts to develop an efficient groundwater transport and remediation model, referred to as REMChlor-MD, which takes into account subsurface phenomena such as matrix diffusion in the Plume. Dr. Ron Falta from Clemson University and Drs. Chuck Newell and Shahla Farhat from GSA Environmental will give a joint presentation introducing matrix diffusion and modeling approaches, detailing REMChlor-MD capabilities, and providing comparisons between laboratory experiments and analytical solutions. We will pause roughly midway through their presentation for a short Q&A session, and we'll conclude the webinar with a longer interactive Q&A session with our three speakers. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. The most compatible browsers to use are Firefox, IE, or Edge. If you lose the content on your screen, or if your screen freezes, try keying in Control F5 to perform a hard refresh. If you're accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use this chat box only for comments related to technical difficulties. The Q&A option on your screen should be reserved for questions for the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we do encourage you to submit questions well in advance of the Q&A sessions. Just remember, when submitting your questions, please add your organization name at the end of the question so that we can identify you during the Q&A sessions. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of CERDP and ESCCP, as well as the Program Manager for Environmental Restoration. Andrea has been with CERDP and ESCCP since 2001, and before that, she was a research scientist at Battelle Memorial Institute, where she conducted research on in-situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea?
Thank you, Rula. Slide 9. Before we turn you over to the main webinar today, I'd like to just give you a little overview about CERDP and ESCCP and why we're doing what we're doing here. Very quickly, CERDP is essentially our R&D program, the research and development. It's been around since 1991, and this is where we're looking at fundamental to applied research to really look at real-world environmental management as some of the DoD's biggest challenges. ESCCP is our sister program, and this is our demonstration validation program, and often the knowledge or technologies that are developed under CERDP, once they have matured and are ready for the field, they will migrate into ESCCP and be used to fully demonstrate the technology in a real world situation. Slide 10. We have two broad drivers for our programs in terms of what we tend to fund and really investigate. The first is sustaining our testing and training ranges, facilities, and operations. And shown here are a number of the various areas that we investigate, and you can see this is very broad, from looking at sustainable forward operating bases to maritime sustainability to noise issues, etc. So we have a very broad range of issues that we need to address. Slide 11. The second driver is reducing our current and future liability, and this involves both the contamination from past practices, and the topic of today's webinar is really addressing much of this issue of contamination from past practices. But we also look at pollution prevention to control life cycle costs. Slide 12. We invest a tremendous amount of time in developing these various technologies, so it's very important to us to transition these technologies to end users. Slide 13. And in doing this, we have a number of different methodologies that we use to try to reach the end user. This can take the format of various videos that are posted on our website. We have in-person training. We have many different guidance and manuals, as well as our EnviroWiki, which is up on our website. And then finally, we also use these webinars as a way to transition the technologies out to the people who will eventually use it to manage their sites. Slide 14. Shown here are then a number of the upcoming webinars with registration now live on our site. And again, here you'll see we have them roughly about twice a week. The range of topics is pretty enormous, and we cover all of the different areas that we fund and under CERTIP and ESTCP. Slide 15. You can access summaries of the webinars that are upcoming, as well as registration information here. And also here you can see the archived webinars that we've been doing for the past couple of years. And the slides as well as the audio is all archived if you want to go back and see information. Slide 16. And before I let you go into the webinar today, I do want to mention our symposium. We have our annual symposium every year. It is a fantastic way to get information about everything we're funding. Everyone we fund comes and at least presents a poster about their work. And of course, we also have platform presentations that focus on different areas of interest each year. This year, we will be at the Washington Marriott Wardman Park on December 3rd through 5th. Registration is not quite available yet, but it will be very soon, and I hope to see you there. So at this point, Rula, I'll turn it back to you for our webinar.
Thank you, Andrea. And it is now my pleasure to introduce today's first speaker, Dr. Ron Falta. Ron is a professor of environmental engineering and earth sciences at Clemson University in South Carolina. He has served as a PI on multiple R&D grants, focusing on subsurface remediation and mathematical model development for sites contaminated by chlorinated solvents. Ron has authored more than 60 peer-reviewed research papers and book chapters in a number of related areas. He earned his bachelor's and master's degrees in civil engineering from Auburn University and his doctoral degree in mineral engineering from the University of California at Berkeley. Ron?
Thanks. So today we're going to talk about this new matrix diffusion tool that we've been working on as a part of the ESTCP project. And we've divided this into a couple of parts. So I'm going to give the first part that gives the background of this method, simplified method for modeling matrix diffusion and some testing. And then we'll switch over to Chuck and Shahla, and they'll show the interface and how to use this tool. So for the agenda, I'll start off with kind of a brief introduction to matrix diffusion and then the standard, if you will, modeling approaches, but then focus on this high-resolution semi-analytical method that's used in the REMChlor-MD. And then I'll show several different test results for matrix diffusion in Aquitard. These are comparisons with analytical solutions, and then comparisons with analytical solutions and experiments for matrix diffusion in both fractured and heterogeneous systems. And then we'll shift over to Chuck and Shahla, who will talk about how to use REMChlor-MD and the interface, and then we'll wrap this up. So This is just an idealized picture of a DNAPL site. There's a DNAPL plume here that's extended down through the water table to a clay layer. We have groundwater flowing through that, creating a plume. And historically, we've focused on how to clean up the DNAPL source and how to treat the plume in different ways. But there's an additional mechanism that's very important, and that is diffusion of dissolved solutes into low permeability zones. And that can be an underlying clay layer, or it could be embedded low permeability heterogeneities, or it could be unfractured parts of a fractured media. So this has really received a lot of attention, I think, in the last 10 or 15 years. The idea is that you have solutes that move in high permeability zones, but they have a strong interaction with adjacent low permeability zones because of the high concentration gradients. So if you look at this panel, as a solute moves through the high permeability zone, the high concentration gradient results in forward diffusion into the low permeability zone that's adjacent to it. And then if you do remediation and clean out that high permeability zone, you reverse that concentration gradient. And now you can have a back diffusion process that can recontaminate that high permeability zone. And Beth Parker and Steve Chapman and others have shown through modeling and examination of field data that this process may last for at least many decades, if not perhaps centuries. So it's something that in certain settings could dominate the contaminant transport and remediation. So when we think about the settings where matrix diffusion can occur, there has to be a contrast in hydraulic conductivity or permeability. The simplest system would be an aquifer Aquitard system, just with a homogeneous transmissive zone adjacent to an Aquitard. And in that case, you could have diffusion down into the Aquitard, and that could be significant after the transmissive zone is cleaned up, with back diffusion coming back out of that low permeability zone. A more complicated system would be one that also has low permeability layers. So looking at the second panel here, in which case you would have matrix diffusion happening in these low permeability layers in perhaps a sedimentary system. A more generalized system would be a heterogeneous system that has low permeability zones of different shapes and sizes, and a range of shapes and sizes. And then you would have matrix diffusion in and out of those zones, as well as with matrix diffusion in an underlying low permeability zone. And then the most extreme setting would be a fractured porous media, such as a fractured sandstone or limestone, where you would have flow through the fractures and relatively high velocities in the fractures, but then relatively large unfractured matrix blocks, but large amounts of matrix diffusion between the fractures and the matrix blocks. And that really probably represents the most extreme geologic scenario for matrix diffusion. So in all of these, we would like to model that mass transfer, but it's not that easy to do it with current numerical models. And it has to do with the scale at which these processes happen relative to the scale of at which the grid blocks are discretized. So it can be done, though, and there's been some nice work done in this area. A classic paper was done, I guess, about 6-7 years ago by Steve Chapman and Beth Parker and Tom Sale and Leanne Donner, where they looked at, among other things, at these experiments that have been done at Colorado State. Probably a lot of you are familiar with that. Leanne Donner and Tom Sale did this sand tank experiment that's shown in this top center panel, where they had a sandbox that had clay inclusions, clay lenses in it, and then they flushed from left to right that sandbox with the different solutes, including a fluorescein dye. And then after several pore volumes of that dye being flushed through the sandbox, then they flushed it with clean water. So there was a loading period and then a long period where it was swept with clean water. And it shows a very strong matrix diffusion effect. And what Steve Chapman and Beth Parker and the others did in this paper is showed that you can model that with a conventional numerical model, finite difference or finite element approach. You discretize those low permeability zones explicitly, but in order to accurately do so, it requires a fine discretization at the scale of roughly centimeters or even less. So you can do that, for a small problem like this. It becomes a little more problematic if you try to do this at the field scale in 3 dimensions. It just winds up being a very large model. So they had a comment here, which I agree with, that numerical modeling requires much higher resolution than would commonly be practiced to simulate matrix diffusion. And the reason for that is because matrix diffusion is controlled by concentration gradients that happen at the millimeter to the centimeter range. But when we model a large field site, our grid blocks would normally be tens of centimeters or maybe even several meters. So practically that means that we have to somehow account for matrix diffusion processes that are happening at the sub-grid block scale if we want to use a reasonably fast model. So that issue has motivated this work. If you look at screening level models, so by screening level, I mean these analytical solutions like BioScreen, BioChlor, AT3D, and REMChlor, really none of those screening level models consider matrix diffusion in the plume, and they really don't consider it in the source, although REMChlor can sort of approximate it. So these existing screening level models don't consider it at all. The numerical models can consider matrix diffusion, but only with a fine grid, a computationally intensive grid. So that is what motivated this work that was funded by ESTCP. This is a program called REMChlor-MD. It's essentially an update of the original REMChlor model, but to include matrix diffusion. So this is a free model, screening level model, has the same kind of template as the original REMChlor, where you can approximate source remediation at any future time by removal of some fraction of the source, and you can approximate plume remediation at any time by manipulating the reaction rates in space and time. So the reactions in the plume are first-order parent-daughter reactions, and the key assumption in this model is that the flow field is 1D, constant, and linear. So it's the same kind of flow field as in BioChlor and REMChlor. But the difference between this model and those earlier ones is that it simulates matrix diffusion, and that requires us to use a numerical approach, which is conceptually similar to what's used in the larger programs. But what's different here is we have the semi-analytical approximation for matrix diffusion embedded in each grid block. So this program considers diffusion into Aquitards as well as into heterogeneous and fractured systems. And it also has the parent and daughter compounds with independent retardation factors and independent reaction rates in the transmissive and non-transmissive parts of the aquifer. And those reaction rates can also be manipulated in space and time to simulate different remediation actions. So the semi-analytical method was actually adapted from the petroleum engineering field. There's a classic paper by Vincent and Westerfeld from 1980 where they developed this elegant method that's relatively simple for modeling heat conduction into cap rocks in oil reservoirs undergoing thermal treatment. So this panel on the left is showing the concept, a reservoir with hot water in it, hot fluids in it, adjacent to an impermeable cap rock. There's a conductive heat loss that is significant that they would like to simulate. And back when this was done in 1980, computers were, of course, thousands of times slower than they are now, so they didn't want to have to discretize that cap rock. So they came up with this method, and it's fairly widely used in geothermal reservoir engineering. So if you think about our problem, on the right side, we have an aquifer with dissolved constituents, chemicals, and there's a diffusive process into an Aquitard. And the mathematics of that process, if you look at the differential equations that are shown below here are really similar. They're analogous to each other. The differential equation for transient diffusion looks like the equation for transient heat conduction, with the only real difference being the addition of reaction terms in the matrix diffusion problem. So it seemed like, you know, there was a good chance that this method could work for our problem, and it turns out that it works very well, I think. So this method conceptually is similar to dual porosity in that you take each grid block and you think of it as having two parts: a high permeability part through which you have advective flow, and a low permeability part that has a matrix diffusion interaction. The difference, though, is that the semi-analytical method has a much higher resolution of the concentration gradient and therefore the diffusive flux, and it's also a little bit more efficient. It's also similar in a lot of ways to what's called the multiple interacting continuum method that's used in multi-phase flow models sometimes, where grids are locally subdivided in one dimension. So that would give a similar result to this. But the basic idea with this is that we use this equation at the bottom of the slide here to approximate the concentration profile in the low permeability zones in every grid block. So that concentration profile is equal to the concentration in the high permeability zone, which is this first C term here, plus this polynomial that depends on the depth into the low permeability zone, multiplied by a negative exponential that also depends on the distance into the low permeability zone. And the key to this method is that there are two adjustable parameters here, the P and the Q. And I'll show how those are calculated, but those are adjusted in every grid block at every time step to track what this concentration profile looks like so that we can model the matrix diffusion. So the hard work in setting this up is figuring out the P and the Q, but that's really a calculus problem. And once that's done, it's just programmed, and then it never has to be done again. They could just be calculated. So without getting too bogged down in the details, the parameter P and Q in that fitting function come from the differential equation for transient diffusion and from a mass balance. So there's two constraints that are used. The first one is that we want to satisfy the differential equation for matrix diffusion with reactions at the interface of the low permeability and the high permeability zone. So that is what the first equation here is expressing. And so you plug in that expression for C and you take these derivatives and you get an algebraic expression from this. The second constraint is a mass balance. So the rate at which mass changes in the low permeability material has to be equal to the rate of diffusive flux across that interface minus the rate at which the contaminant is decaying plus the rate at which it might be produced by a parent compound. And so that gives this second equation. And the integrals here have to do with the fact that we're calculating the mass in the low permeability material. So we're going from the surface at 0 to a distance L. And if we're looking at an Aquitard, that L could be very large or even infinite. If we're looking at finite heterogeneities, that L would be a characteristic maximum half thickness or a characteristic diffusion length. So if you had parallel fractures, that L would be half the distance, half the fracture spacing. That would be how far on average the contaminants would diffuse. So that's how the geometry, partly how it comes into play here. So again, this results in another algebraic equation, and then you can solve algebraically for P and Q. And then, as I said, that's what goes into the program to calculate that concentration profile. Oops. So then the next step is to apply Fick's law of diffusion. So the equation is shown here. It's just modified for porous media. So the diffusive flux is just equal to the concentration gradient times the diffusion coefficient times the tortuosity and porosity. And then if we substitute in that trial function, we get the expression that's shown in the second equation here. And so the diffusive flux then with this method is just a concentration dependent source sink term. So the diffusive flux really winds up only depending on the current concentration in that grid block multiplied by a constant plus another constant. So for that reason, it's very efficient, and all these things are updated at every time step, but it winds up, once the algebra is done, being a relatively straightforward thing to get this into the program. So as far as the model parameters required to apply this method, if we're looking at matrix diffusion into an Aquitard, that's pretty straightforward because we know the surface area of the Aquitard and we know that it's typically would be relatively thick. But if we have embedded heterogeneities, then we need to have three geometrical parameters. So the first one is the volume fraction of the high permeability material. So what fraction is the water flowing through and what fraction is low permeability. The second parameter is the interfacial area between the high and the low permeability zones in that grid block. And the third would be this characteristic maximum diffusion length, which would be like the half the fracture spacing or the average half thickness of low permeability layers. These second two parameters are related to the first one through a volume balance that's shown in this equation. If you think about the volume of low permeability material, that would be expressed on the left-hand side, and then that geometrically should be equal to the product of the interfacial area and the average diffusion length. So by using this consistency equation, we're able to reduce the three parameters down to just two. So really, you need to know the volume fraction of high and low permeability, and then an estimate of either the interfacial area or this characteristic length, and then you could use that equation to get the third parameter. So now I want to move on to different tests that we've done with the model. I'll start with the simplest geometry that we could have. We have an aquifer and we have an Aquitard, and there's going to be matrix diffusion from the aquifer into the Aquitard. But we're going to model this with just a single grid block, and the entire interaction in the Aquitard is going to be done with this semi-analytical method using this trial function that I've described. So this particular problem is going to involve reactions in the Aquitard using the semi-analytical method. And the setup is that at time zero, we'll put 100 milligrams per liter of tetrachloroethylene into the aquifer, and we'll maintain it at that concentration. And we'll keep it at that concentration for 50 years. And then after 50 years, we could flush it. But then we're going to have matrix diffusion into the Aquitard, and then once the PCE diffuses into the Aquitard, it can degrade into TCE, DCE, and vinyl chloride, and then that's all being done with the semi-analytical method. So here's the result after 50 years of diffusion. So we're looking at a plot of concentration versus depth into the Aquitard. So the aquifer is on top here, and it's being maintained at 100 milligrams per liter of PCE. So over time, after 50 years, the PCE is diffused in, as this blue line shows, but it's decaying with a 10-year half-life, and it decays. As it decays, it's producing trichloroethylene, which is shown as the red curve. And as the TCE decays, it's producing DCE, which is producing vinyl chloride. So we're getting all the daughter products being produced in the low permeability part by this semi-analytical method. And there's an exact analytical solution for this case, and that's shown as the dashed lines. So the two are very similar here. And one interesting thing about this, in the aquifer, it's maintained with zero concentration of the daughters and only PCE. So there's forward diffusion of PCE, but because it's reacting to form TCE, there's actually back diffusion of TCE back out of the Aquitard in this case. So now I want to show a different kind of comparison. This is based on a series of laboratory experiments that were done at the University of Florida a few years ago by Minjun Yang and Jim Jowitz and Mike Annabelle. These involved a laboratory sand tank that has a several centimeter sand layer and then a relatively thin clay layer, 6 or 8 centimeters. And the experiment consists of injecting water with a tracer through the sand and producing that from the other end, and then doing that for several pore volumes, between 5 and 15 pore volumes, and then following that with clean water for about 15 pore volumes. So you can measure the breakthrough curves during the loading period and then during the unloading period. So to model this, we set up a one-dimensional grid where we just divide this into slices. And so it's just a one-dimensional flow, and each grid block has a certain fraction of sand and a certain fraction of clay, but the water is all flowing through the sand, and the entire interaction with the clay is being done by the semi-analytical method. So in this case, we know the exact geometry. We have good estimates for the parameters. And so without any calibration, we ran this, and these are comparisons with the experimentally measured breakthrough curves. So the experimental data are the circles, and then the simulated concentration at the outflow is the solid line here. So it matches, I think, pretty well. And again, there's no calibration. All this was done just through the geometry of the problem. And this model runs in a fraction of a second. So a more extreme case of matrix diffusion, I think, is the fractured rock case, because of the large surface area of the fractures and the very, very small volume of the fractures. Matrix diffusion has a really strong effect on concentrations in the fractures. And there's a well-known analytical solution for the idealized case of parallel fractures. This was developed by Siddiqui and Friend back in the early 80s. I think it's known as Crayflush. So this analytical solution can consider parallel fractures where you have advection and dispersion in the fracture with retardation and decay, and then you have perpendicular molecular diffusion and decay and retardation in the matrix. So did a comparison of this new method with the analytical solution. So I set up a test case where we have parallel fractures that are half a meter apart, but each fracture has an aperture of only 100 microns. So, roughly the aperture is the width of a human hair. So a very small fracture volume compared to the matrix volume. So this is a case where you'd expect large matrix diffusion effects. And there's significant porosity in the matrix. The velocity in the fractures in this example is 100 meters per year. So in the absence of matrix diffusion, the solute would move through the fractures at 100 meters per year. So we introduce a contaminant at time 0 at 100 milligrams per liter and maintain that for 50 years and then flush it with clean water for 150 years. And to model this, again, we have a model of the fractures in the matrix, but the flow is only happening in the fractures. And so we can model this with a one-dimensional grid, but then this interaction, the matrix diffusion, is being done by the semi-analytical method. So the graph on the right shows a comparison with the Siddiqui and Friend solution at different times. So this is showing the predicted concentration in the fracture at different times. So the first blue curve here is at the end of the 50-year period. And what you'll see is that the solute's only moved about 20 meters from the source. So, considering that the water's moving at 100 meters a year, there's a really profound retardation-like effect because of the matrix diffusion in this setting. Then when you reverse or start to flush this with clean water, you get the remaining curves. And so now the solute's being very slowly flushed out of the fracture. And the reason it's so slow is from the tremendous back diffusion that's coming out of the matrix. So these curves that go out to 200 years are are showing that even after 150 years of flushing, you would still have about 25% of the original concentration in the fracture, and that's entirely due to the back diffusion. So in this picture, the colored lines are from the semi-analytical method, and the black dashes are the Sudickian-Friend model. So it compares very well in this case. And if you plot this on a log scale, the comparison still looks good down to very low concentrations. This is a comparison with the experiment that was done at Colorado State by Leanne Donner and Tom Sale, that I described earlier. So they had the sand tank with the low permeability clays, and they flushed it with fluorescein and other tracers for a period of days, and then followed that up with clean water. And as you can see in this lower panel, there's a very strong matrix diffusion effect that occurs because of that. So we modeled this again using just a one-dimensional grid. So this is cut into slices from left to right. And in each grid block, there's some sand and there's some clay, and those proportions are determined from the proportions of sand and clay in the experiment. And so this geometry is more complicated, but we used just averages. So we were able to measure the area of these and then use that equation I showed a little bit earlier, the consistency equation, to estimate the characteristic average thickness. And so then we can run this without any calibration, just based on average geometrical properties. And again, all the matrix diffusion is happening by the semi-analytical method. So without any calibration, these are predicted breakthrough curves of bromide and fluorescein. These two compounds have slightly different transport properties because of different diffusion coefficients and retardation factors. But again, the uncalibrated 1D model does a reasonable job, a fairly good job, I think, of calculating these breakthrough curves from that experiment without, fine discretization. This is still a coarse discretization. So I want to finish up my part by showing some larger fine grid simulations that Noelia Muscus did for her master's thesis last year. These were done with MT3D and ModFlow. So we set up this numerical grid with almost 3 million grid blocks, generated this heterogeneous system using the TPROGS program within GMS. So this is a sand clay system. The clay is very low permeability. The sand is moderate permeability. And we have a long correlation length horizontally and a short correlation length vertically that gives us these lens-like features that are spread throughout this model. And so we set this up, and then we run ModFlow. We impose a head from left to right, so water flows through this. And once we have the water flow, then we run MT3D, and we introduce a source in the center of the grid at the upstream end. And so that source is simulating a DNAPL source, and we leave it there for about 30 years and then remove it. And then we look at the advection and diffusion through this grid over a couple hundred years. So as we're modeling the transport in this heterogeneous fine grid, we set the dispersion coefficients essentially to 0, and all we have really is advection and diffusion. But you get a dispersion-like effect from the heterogeneity, spreading the solute out, the TCE out. And then there's a very dramatic effect of matrix diffusion into the clays from the large surface area. So this first panel shows after 30 years the dissolved concentrations in this model, the sources on the left here. And then at 30 years, we remove that source and flush this with clean water. Well, on the right side, we're looking at this after 100 years of flushing, and really, essentially, the plume is still there. So it's lower concentration, but it has almost the same footprint. And that's because of all the matrix diffusion that happened into the clay, and now it's a very slow back diffusion process. So this simulation is really dominated by matrix diffusion, at least the timescales are. So next, we repeated this using the REMChlor-MD program. we used a much coarser grid. So instead of 3 million grid blocks, we used 7,000 grid blocks. The fine grid model had 400 layers. This model has 18 layers, and it's homogeneous. So it's a much, much simpler model. We have to use a macro scale dispersion to get that kind of spread that was caused by the heterogeneity. So that's kind of a conventional dispersion approach. But then the matrix diffusion here is being simulated in every grid block with the semi-analytical method that I've described. So the 3 matrix diffusion parameters that we need for this, we estimated by sampling the grid. So we pretended like we were drilling boreholes through that 3-dimensional grid, and then we could see what, you know, the vertical distribution of materials look like, and we could calculate an average volume fraction and characteristic length from that, and then estimate the area. So we do that and then run the model. It runs in about 13 seconds, whereas that fine grid simulation took a few days to run the transport part of it. So I'll show some comparisons here. These are cross sections through the different models at different times. So the top panel is after 10 years, the top 2 panels. The top one is showing a slice, vertical slice through the MT3D model. The lower one is showing the REMChlor-MD semi-analytical model. With a heterogeneous grid, it's kind of hard to pick a representative slice at early time because they all look different, but it starts to average out some after 30 years. So if we look at the fine grid numerical simulation and then the very coarse grid REMChlor-MD simulation, they look more similar. And then after the 100-year flushing period, we can look at the same slice, and you can see they have similar concentrations in the two and similar distributions. If we look at the same problem from a top view, now slicing through the center of the DNAPL source at that elevation, again, here's a comparison of the 2 methods. So at 30 years, this is the end of the loading period. We have a core of high concentration and then a significant plume of still fairly high concentrations. And then we flush this for 100 years and we still have a plume, although at lower concentration, but the concentrations and the shape are fairly similar here. But a more quantitative way to look at this is to look at the mass discharge at the outlet face. So the mass that is exiting the model at the downstream side. So in this slide, we're showing the mass discharge. This is in kilograms per year as a function of time. The open circles, or the circles here, are from the MT3D simulation. And then the green curve is from this REMChlor-MD simulation with no calibration. So we just estimated those parameters by sampling the grid in the way I described. And I feel like it does a pretty good job of matching, considering there's not any calibration. You can adjust it a little bit, and it does a little bit better. So the orange curve, we tried to calibrate it by adjusting that characteristic length, but it's a little bit better. But I think they're both pretty good, considering the simplicity of this. So the final thing I want to show is another case that was done the same way. The only difference is that the heterogeneity is more random here. So it's a shorter correlation length, same number of grid blocks and so forth. And again, we calculated the parameters in the same way. So here are the vertical slices at different times, showing the comparisons. So I feel like they compare pretty favorably. This is the end of the loading period. Down at the bottom, this is after 100 years of flushing. That's a cross-sectional view, and then here's a top view. So there's a lot of lateral dispersion in this case because of the way those heterogeneities are arranged. But the overall concentration patterns, and particularly during the flushing period, are pretty similar between the 2 models. And again, the REMChlor model has less than 10,000 grid blocks and runs in a few seconds compared to many, many hours for the fine grid simulation. And then finally, here's another comparison of the mass discharge at the downstream face. So the circles are the fine grid simulation The brown line is the uncalibrated REMChlor-MD result, just using the estimate from the, a few samples or some samples in the grid. And then the darker line is a calibrated one where that characteristic length has been changed by about 10%. So those are the comparisons. This program is now available for free from the ESTCP website. We have a over 100-page manual that goes through the mathematics and the theory and shows some of these examples. It has a lengthy explanation of all the input and output variables. There's chemical and geological parameter databases for helping the user estimate what to use, and there's some case studies and several appendices. So with that, I think we're at the end of my part of this.
Great, thank you so much, Ron. As a reminder for our audience, you may submit questions by using the Q&A box on your screen. We have received a number of questions on the first portion of the presentation that Ron will answer. Ron, under what general conditions is matrix diffusion likely to be important and similarly not important?
Well, it really depends on three things, I think. The first thing it depends on is what is the range of concentrations that you're dealing with. In other words, what's the maximum concentration in the source and in the plume when the release happened, and how does that compare to the regulatory standard? So if you have something like trichloroethylene where you could have 1 million micrograms per liter and a regulatory standard of 5, then any amount of back diffusion could be significant. But on the other hand, if you had some other contaminant and you're only like 10 times above the regulatory standard, well, maybe in that case, matrix diffusion would be a lot less significant. The geologic setting, you need to have a contrast in hydraulic conductivity between the materials. And then if it's a fractured system, the unfractured rock has to have a significant porosity. So a crystalline, metamorphic, or igneous rock would have less matrix diffusion than, say, a sandstone or a limestone.
Great, thank you so much. With respect to use in fractured rock settings, velocities could be much higher in fractures. How do you explain observations of some long plumes in fractured rock settings, for example, MTBE plumes, if using this model?
Well, the model predicts short plume in the fractures if the fracture volumes are small and the matrix volume is large, and if there is a large porosity. So I guess in order for that to happen, the fractures would have to have large apertures, or the matrix would have to have lower porosity, is what I would say.
Great, thank you. We have a question related to slide number 37, and that question is as follows. For the fractured bedrock system shown on slide 37, how would far fewer fractures, such as every 20 meters, affect diffusion?
You get even more diffusion the further they're spaced from each other. Because if the fractures are closely spaced, you get this intense matrix diffusion for a while, but then it kind of fills up the matrix because of the short distance that it has to diffuse over. And then during the unloading period, it comes out quicker as well because of the short distance. So in a way, it's a more intense but shorter lived phenomena when you have close fracture spacing.
Great, thank you. Is there potential to incorporate monode form biological reactions in future semi-analytical models, or are we limited by the analytical solutions available?
I would say maybe. if you go back to the equations that I showed where the P and the Q came from, I mean, as long as you can express the reactions in an equation like that, and then take the derivatives and calculate the integrals, I think you should be able to use this method, but I haven't attempted that yet. So I say maybe.
Maybe. All right, that's fair. And then a few other questions for you. Could aggressive vertical hydraulic flushing, if possible in a heterogeneous environment, be simulated by REMChlor-MD?
Not really, because REMChlor-MD is just assuming a linear horizontal flow field. So yeah, it's just not built for that, I don't think.
Okay. How sensitive is the model to the input of the high permeability material fraction? In other words, how well do we need to understand the lithology to be able to get a reliable model output?
Yeah, that volume fraction affects the results in a couple ways. In one way, it affects the effective velocity of the solute, because if you have a small volume fraction of high permeability material, but you're forcing a large Darcy flux through that, that means that the actual velocity has to be pretty high. But then it also affects the relative reservoir of mass that's available for matrix diffusion. So there's kind of two effects. As far as how well you would need to know it, I guess that depends, but it would be a big difference between 50% and 20%. It may be a small difference between 20% and 30%, if that helps.
Yes, thank you. All right, and one last question before we move to the second portion. This is a question from the Army Corps of Engineers in Baltimore. Are there other elements we should measure during field work to best characterize matrix diffusion? What is your recommendation on that?
Well, the main thing we want to know would be through what volume is the solute moving by advection, and through what volume is the solute not able to really move by advection. Now, that's a simplification because there's a continuum, but in this kind of a model, that's the way it's broken up. And then from that, you can make an estimate of what the interfacial areas look like. If you could calculate the volume fraction and this characteristic thickness, then that's the main thing that's needed. And actually, Chuck and Shahla are going to show how we have a tool for estimating that in the interface.
Wonderful. Thank you, Ron. This is a great transition to the second portion of today's presentation, which will be delivered by Chuck Newell and Shahla Farhat from GSI. Chuck is a vice president at GSI Environmental in Houston, Texas. He is a member of the American Academy of Environmental Engineers, an NGWA certified groundwater professional, and an adjunct professor at Rice University. His professional expertise over the past 30 years includes site characterization, groundwater modeling, non-aqueous phase liquids, risk assessment, natural attenuation, remediation, environmental software development, and long-term monitoring projects. Chuck has a bachelor's degree in chemical engineering and master's and doctoral degrees, all from Rice University.
Shahla is a managing scientist at GSI in Houston, Texas. She specializes in environmental research and engineering with a focus on the assessment and remediation of local and regional groundwater aquifer systems, fate and transport modeling, and decision support systems. And Shahla has served as co-PI for several ESCCP projects over the past 10 years. Chuck and Shahla, please proceed.
Okay, well, this is Chuck Newell here, and we're going to first go to the splash screen, the main screen of the model. So if we're looking at this, let's see if I can get it fired up here. We more or less show the intro screen, and the main thing one of the main things I want to talk about on this one, of course, another amazing ESTCP product that's out there. So funded by ESTCP, help solve these difficult environmental problems. But what we're going to do, what Shahla and I are going to do over about the next 15 minutes is just give you a quick tour of the interface that runs this model. And Shahla, just a quick question, is there going to be a lot of math, partial differential equations in our talk?
No, but there's going to be some geology.
A little bit of geology. And so the main theme here is that Dr. Falta, he developed this remarkable code based on all those partial differential equations of this Fortran code. And this interface goes on the front and the back, where you translate your site information into a series of key variables. You put it in there, and then you can see the output that's in there. Shahla, the interface is written in Excel, is that right?
That's correct. It runs on Excel 2016.
Okay, well, if we went ahead and we're getting ready to start, then you'd click this button here, right?
Yeah, but before we go on, Chuck, do you want to tell the audience what the graphic stands for?
Oh yeah, so the graphic is basically, I think, Dr. Falta's slide 22 reimagined with a little less orange and more red. But it says if you've got this site with these different geologic conditions, then you can simulate that now in this code. You can do these Aquitard type of situation on the top left panel. You can do a layered system over here. On the bottom left, you can look at heterogeneous systems with clay lenses, silt lenses, things like that. Or you can do fractured rock, and so that's the key part that's in there. But let's look at the, if I hit start, then that's going to take us to this screen right here, the main input screen, right?
Right, and to run REMChlor-MD, you need, the key data inputs that you need are model configuration information, you need media characteristics, matrix diffusion information, the contaminants and source term information, plume degradation, plume transport, source zone remediation, and modeling parameters. Okay,
a lot of white cells in here, and that's the input data you need. Is this sort of almost all of it? If you get through this page, is that sort of the most of the model input task?
Almost all of it.
Okay, and so if you if you run REMChlor before, some of the stuff's the same. What's the same as the old one?
Right. Yeah. So it does have some similarities. So the hydrogeology is similar, the plume degradation and the source remediation are similar to REMChlor.
Okay, how about what's new? What's the new part in the model?
REMChlor-MD is built on a modeling grid, so that's new. That's totally different from REMChlor. And also you need to enter information on the media characteristics and obviously matrix diffusion.
Okay, we're going to show some more of that in a minute right there. But let's just try to get a sense here. There's these, you got to fill in the numbers, the white box. Let's say I've got a remedial investigation report on my desk or it's on my screen. How long would it take to mine that report and put the data into the model and get a run out?
It doesn't really take that long. So if you have all the data, then from start to finish, it'll take you a couple of hours.
Okay, well, let's now focus on going into it, and we're going to now go into sort of this geology part, and we're going to look at what we call the heterogeneity calculator. And so this is either two-step or three-step process if you're an unconsolidated media. And this is the first one, and it has these different boxes here. I call this the Denny's menu approach, where you look at your site and you're going to identify here, do I have an Aquitard on the top or the bottom or both or none? And so, for example, I've worked at a site in Cape Canaveral where I would pick the left one. There's really not any of those Aquitards in there. Other ones, in the Houston, Texas area, yeah, there's these thick clay layers on the top and the bottom. I'd pick the far right one. But this is step one, where we're sort of defining these boundary conditions, and that information then goes into the code that Dr. Falta wrote. But now we've got to do step two. Let's take a look at that. And what's going on here?
So to make it easy for the user, REMChlor-MD provides three options of calculating heterogeneity at a site. The first one is the simple option. So this is based on your understanding of your site. You can estimate the thickness of the embedded loci layers in the transmissive zone as 0%, 20, 40, 60, or 80%. Then you select one of those radio buttons, provide an estimated or a typical thickness of the embedded loci zones, and REMChlor-MD does the rest.
So that's the first option for step two. You got some other options?
Exactly. So for the second option, you can use boring logs to calculate site-specific heterogeneity parameters. And then the third option is if you already have those three numbers, then you could just enter them directly.
Okay. So sort of a quick and dirty way, which is the Denny's approach, one of these 5 options, or you can calculate them yourself, or you can use this next part, which is the actual going in and looking at stuff on boring logs. So let's look at this. And here we've got an example boring log, and it may have an Aquitard. We say, no, you're not going to include that in this step because you've already done that in step 1. But this says I've got these 3 units, and what do I do with the data in this boring log? how do I transfer it over here?
So you need the plume top and bottom information, first of all, and then for each boring log, you write in or you estimate the thickness of the interbedded locate layers, and you enter up to 10 different thicknesses.
And I'm limited to one boring log?
No, you can enter up to 100 boring logs.
Okay, and then it would average all those, right?
Yes.
But the key thing is the translator between this heterogeneity calculator and Dr. Falta's remarkable model is these three key parameters. What are they?
Exactly. So those parameters are the transmissive zone volume fraction, the average diffusion length, and the surface area of the locate interfaces.
Okay, so if you just put this log data, you don't have to, it will calculate it for you, is the bottom line here. Or you can calculate it yourself if you want. Now that's unconsolidated media. Let's look in fractured media, and how do you enter data for fractured media into the model?
So for fractured media, you basically just need two parameters. You need the typical distance between the parallel fractures and the typical thickness of the aperture or the fracture.
Because if you got this RI report or this fractured rock characterization report, you're going to be looking for that information. And again, it's pretty general. You're not putting in all the different fractures. This is just a representative information about that spacing and that thickness. So, now, what if I've got a site that's got both horizontal and vertical fractures? Can I represent that?
No, this version of REMChlor-MD can only handle parallel fractures in one direction.
But Dr. Falta said more or less, you're still capturing the essence of matrix diffusion. This approach shouldn't make that much difference in the long term that you're having this matrix diffusion work in here. Okay, so again, quick overview. That's the input data. You've got to enter in things like your hydraulic conductivity. You've got to enter in your heterogeneity calculator information. Do I need to look on the internet what the diffusion coefficient is for TCE?
No, the toolkit does provide default values for quite a few of the parameters, and also not only that, but also the user's manual and the interactive help guide have guidance on typical input parameters.
Okay, so a lot of little calculators and help to get through this thing. Okay, but then once you've entered all the data, there's a button called Run, and you hit it, and how long does it take to get the output out?
It doesn't really take very long. For most sites, it'll probably take you just a couple of seconds, and it does take longer if you have a really fine grid.
Okay. And then if it takes a long time, you can reduce it. But the longest run you've ever run was how long?
About a minute.
Okay. And you have a really fast computer, right? But still not something that's going to take a long time. And that's the real beauty of Dr. Falta's invention, is that it just runs really fast, and it accounts for these heterogeneity in your formation. Okay, well, let's look at the output. And so I see here's the output screen. I got a graph. What's going on the graph here?
So you're looking at the graph of the concentration versus distance in the x direction. So on the x-axis, you have the x direction distance, and on the y-axis, you have concentration. And just like REMChlor, you can toggle which constituent you want to see by checking and unchecking the boxes on the left bottom of the graph.
So the different colors, the different constituents. So we're looking at here that the green, I think, is TCE, is that right? And
that's correct.
You see all these daughter products that are in there. Okay. Now, what's going on the right? What are these things over there?
And to make it a user-friendly product, REMChlor-MD gives you two simple mini calculators. So if you enter the X location and the time in the top two white cells, REMChlor-MD will give you an estimate for mass discharge in grams per day and the plume magnitude at that location and time. Now, if you enter time in the bottom white cell, REMChlor-MD will give you an estimate for the mass at that location in both the locate zone and the transmissive zone, and the mass is going to be in kilograms.
Okay, great. Okay, now this is concentration versus distance. Are there other options to see the input data, output data?
Yeah, you have about 7 options that you can look at. So the second option is concentration in the transmissive zone versus vertical distance. You can also look at concentration in the transmissive zone versus time, concentration versus time in an observation well, mass discharge versus time in the transmissive zone, and then finally you can look at mass versus time in both the locate and transmissive zones.
Okay, so let's say I do a run and I click this button right here, mass discharge versus time. This is the output that you'd see right here, right?
Exactly. So here you're looking at mass discharge versus time. So you have time on the x-axis and mass discharge on the y-axis. And in REMChlor-MD, you can toggle between looking at your y-axis on a linear scale or a log scale. So this slide is you're looking at it on the log scale.
And what's this little jog down right here?
That's because in this example, we remediated the source. In the year 30, we removed 90% of the source mass, and that's reflected in the parent compound here.
Okay, great. Okay, that's the quick tour. Now let's do a quick, I think it's a 3-slide case study.
I think we have one more.
Oh, that's right,
slide.
one more output. Let's go through that one right in here. And so here, what we're looking at is the mass in the low K zone, right?
Right.
Versus the modeled time. And so that's in kilograms on that axis there. And you can just see the change of the composition in the low K zone itself. So here's a question about this one before we go to the example. Can you put biodegradation in those low K zones?
Yeah, that's the beauty of REMChlor-MD. You can do remediation or you can do degradation in both the transmissive and low K zones in the plume.
Okay, and they can be different. A high degradation rate in the transmissive zone or no degradation or another rate in that low K zone, right?
Exactly. You have 9 little boxes that you can toggle.
Okay, so now it's time for the case study. Let's look at that real quick. And the question is what, Shahla? What are we trying to answer here?
So we've been trying to look at the effects of matrix diffusion. So we compared REMChlor with REMChlor-MD. And what you're looking at here is a hypothetical site with a decaying TCE source. And we performed source remediation in the year 30 by removing 99% of the source mass. We're also assuming that there's no plume degradation and the retardation factor is 2. Then in REMChlor-MD, in addition to these input parameters, we also assume that matrix diffusion is happening in both the top and bottom layers, and that 40% of the aquifer volume has interbedded low K layers.
Using that Denny's approach, we're saying the top, bottom, Aquitards, 40% in the middle. Now, if you run just the old model without all that stuff, then here's a concentration versus time at our monitoring well that's quite a distance away from the source. But then you've done this mass removal. 99% of the mass has been removed after 30 years, and this is down gradient, and that remediation works really well. Those concentrations plummet from about 100 milligrams per liter, about 100,000 micrograms per liter to these low numbers here, 0.01. So tremendous impact of that remediation is what you see in here. And then it slowly decays because there's that 1% of the source is still left. So this is pretty valuable information about mass removal and how much you get out. And this is what you see, and you say, wow, that remediation has got this really significant impact. But if you put in the green stuff, that heterogeneity, what does that look like?
So the red line here is the output from REMChlor-MD, and it shows the significance of matrix diffusion. Even in the year 100, that is 70 years after you've removed 99% of the source mass, you still have about 30 parts per billion of TC in the plume.
And so there's even more of impact right around that 50-year period when that cleaner water is going past that well. And so it just gives you this different perspective of it. And that's not the same for all case studies. There's some case studies, natural attenuation of a large PCE source. If you run these lines would be a lot closer together. But you can run these models and see where it's important and what the impact it has. Okay, now we're going to wrap up, I think, of our short tour. In conclusions, a new method for simulating matrix diffusion and these Aquitards, these heterogeneous systems, fractured rocks, have been developed by the amazing Dr. Ron Falta. And
that method is now implemented in REMChlor-MD, a new version of the REMChlor source plume remediation model.
Okay, and so now we've got this interface that makes it you can do these simulations with relatively minimal effort on part of the user.
Right, and finally, some exciting news for the diehard ModFlow fans is that in the near future, this methodology will be applied to the 3D ModFlow 6 and ModFlow USG flow and transport codes.
Okay, another ESTCP project. Principal investigator is
Ron.
Dr. Ron Falta. Okay.
And then Dr. Saurabh Pandey of GSI, Alan Lemon of Aquavare, and I are co-investigators.
Great. Okay, looking forward to that one. That one's still a couple of years out, right?
It's a couple of years out, yeah.
Okay, well, let's go to DoD benefits. And I think this is the key one. We talked about you've got this RI report, you know your site. Within a couple hours, you can quickly assess the effect of matrix diffusion in this screening level model.
And you can consider both source and plume remediation in the same model.
Okay. And the model only requires these 2 parameters, really these 3 parameters related to low K geometry. What are the 3 parameters again?
That's the transmissive zone, fracture volume, diffusion length.
Average diffusion length.
And surface area of the low K interfaces.
Okay. And then this model can be run with and without matrix fusion to highlight the impact. So I think to wrap up, this is the last one. This is where you can get more information about this. And this is just this remarkable code. So ESTP must be charging a lot of money for this, thousands of dollars because of all the capabilities. So how much does it cost?
It's free.
Free, free, free?
Free, free, free.
Okay, and this is the link, and I think that's all we have.
Yeah, and you can either use this link or you can Google REMChlor-MD, and the first search option that shows up is the link for ESTCP inserted.
Very good. That's it.
Great, thank you guys. We have a number of questions that have come in, starting with the following. In what format does the model output come in? Is it a text file, a grid file? And is it possible to import the output into programs like Surfer to create Plume maps?
Yes. So the output is in a text file. So yeah, you can export it into any software that you want.
Great,
and the outputs are very similar. Most of the outputs are very similar to REMChlor. So if you've used REMChlor and exported that output data, then this one is pretty similar.
Thank you so much. Does the tool allow you to import observed data so that you could plot simulated and observed data on the same graph or figure?
No, yeah, you can't do that.
We did that with BioChlor and BioScreen, but it's not part of this code right here. So maybe that's another version, but does not do that right now. So you have to sort of do that on your own.
Great, thank you. And Chuck, can you use this model for contaminants other than chlorinated ethanes?
Yes, you can. And so first is you can run it with chlorinated ethanes, you know, TCA. You just have to change which parameter, the yield?
The yield, yeah.
Okay, so there's a little bit of the stoichiometry is a little difference, and we tell you in the manual how to do that. So you can do these chlorinated ethanes, but it's really almost anything that you think is controlled by the advection, dispersion, diffusion equation. You can run it for benzene. Of course, you won't see daughter products for that. You can run it maybe for some metals as long as that redox chemistry doesn't affect you. Run it for dioxane, run it for MTBE, and so it can be used for a wide variety of things. But the matrix diffusion world's really focused on chlorinated solvents first. But at some point we may be more interested as we get to these low cleanup levels. People are maybe saying, well, is matrix diffusion really affecting my LNAPL source or another source?
Right, and if you're running REMChlor-MD for different, not for a daughter product, but like, B tags, you can also enter a retardation factor for each constituent. So it's not just for the parent.
Okay.
Great, thank you. This is a question from the U.S. Army Corps of Engineers. Can you verify which version of Excel is needed? And also if it can be run on both 32 and 64-bit computers?
Yeah, you need Excel 2016, and we do have two versions. We have a version that runs on Excel 32-bit version, and then we have a version that runs on Excel 64-bit.
Great, thank you. And maybe a question that both you and Ron can answer, and maybe we start off with Ron here. What, in your opinion, is the level of experience or background needed to use REMChlor-MD? Ron?
Well, I think you would want to have some modeling background because you have to give grid spacing and so forth. But it's similar to the REMChlor and BioChlor models, but maybe a little bit more complicated because now you have to give it a grid.
And this is Chuck. I'll just chime in. Is that how much modeling is? So do you need to know partial differential equations really well? Well, no, that's sort of in there. But having a little bit of modeling experience can really help. But if you don't have any modeling experience, there's this idea that you can try to learn by doing. Everyone's got to run a model the first time, and particularly if you're in a shop or a place where there's somebody who's done some modeling before. We tried to design it so just not the high-level modelers can run this thing. We want to get this broad audience that can try this and see it. So I would say that that was one of the goals, is to sort of broaden that platform from being a highly specialized modeling team. They're only folks that can do this. We're trying to deliver it so that more people out there in that DoD world and the groundwater world can do it.
And it does come with an interactive help guide that should really help the users.
Wonderful. And that interactive guide can be downloaded from the CERTUP and ESCCP project webpage shown on the last slide. And as a reminder, everybody can download a PDF of the presentation at the CERTUP ESCCP website. Okay, a question about regulatory acceptance, and we'll start with you, Ron. How have regulatory agencies responded to this model? Has it been accepted for use at any sites?
It is brand new, and there have only just been beta testers, so I think it's too early to say that. It is largely has the same capability as REMChlor, which is fairly widely used, but we're just now releasing this.
Great. Well, we'll keep an eye on it and see how it turns out. And Chuck and Shahla, how, you know, in a very non-technical manner, how would you describe this method differently from a dual porosity type model?
Well, I'll take a
stab
at it, but Ron, I think, really has got the technical basis for it, is that there's some similarities and differences. The similarities that both of those approaches, both Ron's method and the dual porosity method, divide up the world into these, where groundwater is flowing and where groundwater is not flowing. But the dual porosity approach is much more limited, that you have to sort of calibrate the rate that contaminants go in and out of a cell, if it's a finite difference model, where Ron's model, you just give it the 3 numbers and it goes in there. And so this model has the advantage that you don't have to do a lot of this detailed calibration, where in these dual porosity models, and where other factors, like if you change the cell size in dual porosity, you can get different answers. But Ron, why don't you speak to that on maybe the more theoretical basis?
Well, the other thing is, depending on the conditions, the semi-analytical method can be quite a bit more accurate, because it represents the concentration gradients in a more detailed way, rather than just having a concentration difference multiplied by a mass transfer coefficient. So it's really a higher resolution kind of model, but has lower computational demands.
Great, thank you both. And then just a question specific to matrix diffusion. Can this new matrix diffusion method be added to other numerical models? I know you've incorporated it here in REMChlor, but can it be added to other numerical models that are being used out there, Ron?
Yes, really, it could be added to any finite difference model that's fully implicit, and probably to any finite element model that's fully implicit. So it just goes in as a concentration-dependent source sink term. So yes, and as Chuck and Shahla mentioned, we have a new project where we're going to be adding it to future generations of the mod flow transport codes.
Thank you. Chuck and Shahla, would you like to add anything to that?
No, I think it's the REMChlor-MD is going to be this sort of simpler approach. Analytical model runs fast, but that with this new ESTCP project that will be out in a couple of years, that Ron's leading with help from Shahla and Sarab Pandey, and then Alan, then we'll have a numerical model at that point that can efficiently do these calculations, and we can start getting a lot more power, you know, with MT3D and ModFlow.
Great, thank you. All right, well, I'd like to thank our speakers for a very interesting webinar, and remind you that our next webinar is on Thursday, February 21st. Dr. Cyrus Jabari from Joint Base Meyer-Henderson Hall and Mr. Bruce Ensley from Dominion Energy will discuss their work on the utilization of advanced conservation voltage reduction for energy savings at DoD installations. Registration is open for this webinar, so please visit the CERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you can please take a moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.